All right. Hi, everybody. Thank you so much for joining today's webinar. Welcome. This is this month's IDQ Quantum Technologies webinar titled Scalable Semiconductor Light Sources from Atomic Quantum Light Sources in Silicon to Scale-Invariant On-Chip Lasers, with our excellent guest speaker, Dr. Walid Redjem. Walid is a postdoctoral fellow at UC Berkeley, where he works with the Conte group in the EECS department as a researcher on quantum nanophotonics. Walid's current work focuses on developing new types of classical and quantum light sources using topological photonics. And today he'll be talking about some of his exciting recent work on silicon integrated quantum light sources and a new scalable surface emitting laser. Walid's work is truly doing a lot to advance the fields of quantum technology, especially when it comes to integration and scaling to large-scale quantum systems. So we are very happy to have Walid joining us today, and we hope you enjoy his talk. So just to mention, we will be recording this session, and the webinar will be available for rewatching, and it should be online tomorrow. We'll also have a few minutes for Q&A at the end of the talk. That will be handled by Felix Bussier, our VP of Research and Development. He'll be handling the questions. I'm Tyle, our product manager for our quantum sensing products. So feel free to ask questions throughout the talk. Type the questions into the Q&A chat box at the bottom of your screen. We'll filter through these and answer these at the end. And any we don't get to, we will try to follow up offline via email if we have your email. So without further ado, Walid, the floor is yours.
Thank you, Tyle, for the nice introduction. So today I will talk about scalable semiconductor light sources. And first, I want to mention a little bit of story. In 1945, during the World War II, the first all-digital computer was invented. But thanks later to the silicon or solid-state transistor, we managed to really pack lots of transistors on chip. Now we are able to make billions of transistors. And so this was for electronics. We have the same trends for photonics, actually. Nowadays, we are able to build entire optics lab on silicon photonic chip using integrated optics, waveguide, and so on. So my work is really to develop the missing thing in integrated photonics, which is light sources. And in that sense, so I worked on two different topics. So the first one is the discovery of silicon atomic emissive center, how we managed to discover them, isolate them, and also how we managed to integrate them into nanophotonic cavity to enhance their photoluminescence. And at the end of the talk, I will also mention how my recent work on scalable single mode surface emitting lasers. So let's start with the silicon atomic emissive center. And I will not, you know that silicon is very bad light emitter. And that's one of the drawbacks of silicon. And this is because of the indirect gap. We necessarily need exchange of a virtual phonon to emit a photon. And that's a very big problem in terms of efficiency of emission. And so people are, there is many ways to overcome this. The main one is to use strain or using silicon germanium alloy, which is very promising. And there is another trend, which is to use point defects, such as substitutional impurity or interstitial impurities. And these defects will trap carriers, so they can recombine radiatively very efficiently. And my work was really on exploring these point defects for quantum technology. So silicon, on the top left, you can see the silicon lattice with the blue sphere being the silicon atoms. And somewhere in this silicon lattice, you can find a defect. Right? You can see two black spheres. So this type of defect is called the G center. and it's 2 carbon bounded to the same silicon lattice. And the fact that you introduce a defect in this lattice, you introduce also localized bands within the band structure. And especially the DG center act as really an artificial atom with a two-level system with an excited state and the ground state. And you can excite this defect by pumping with a above gap or green laser these defects, and in response you will get photoluminescence in the near infrared. And if you are able to isolate only one defect, you can get a single photon source, so only one photon emitted at a time. So this is very promising. So how we fabricate them? So we first start with silicon on insulator. Then we carbon enrich, so we carbon implant the silicon top layer with a given energy and given fluence, and then we anneal. So this will create enriched carbon with carbon substitutional. And then the last step is to irradiate with protons, high energy protons, mega electron volt. And this will create what is called silicon interstitial. And after irradiation, you will create the G center, right? 2 carbon atom bound to the same silicon atom. So we did that actually. So on the top left, you can see the raster photoluminescence scan of irradiated area. You can see where we irradiated with protons, there is lots of signal coming from the sample. And this signal comes from, as I mentioned, G center with a sharp 0 photon line in the telecom O band, around 1.3 micrometer, and along with the phonon sideband. So this phonon sideband, so on the top, in the bottom right, I plotted the same spectrum, but on log scale. You can see this phonon sideband, which is due to phonon interaction. So you can relax with some of the energy of relaxation can go to a phonon. And in general, you don't want this. You just want a very monochromatic, bright emission. So I will show you how you can manage it how you can manage to remove this phonon sideband by embedding the center into a nanophotonic cavity. So if you look just away from the irradiated area, so the irradiated area contains a lot of G centers. But if you just look away a little bit, you can see discrete spots on the sample. And I zoom here and again, and you can see like a diffraction limited spot. And you can think, oh, maybe this is a single center or a single photon source. So what you do is to measure the second order autocorrelation function, the G2. And basically the G2 will measure the correlation between 2 consecutive photons. So the way we use it, we do it, so we just, it's called ambient twist interferometer with a simple beam splitter with 2 detectors, single photon detector. So here we use a superconducting nanowire single photon detector, and we measure the correlation between the 2. And actually, when you measure, we see a clear anti-bunching at 0 delay, which means that we are really dealing. So this thing is really a single photon source. So this is the first observation of anti-bunching or quantum light emission, deterministic quantum light emission in silicon. And actually, it is quite bright. So we measure the light curve. So we get up to 9,000 count per second, so 9,000 photon per second, with a lifetime of 33 nanoseconds. So with this number, we can actually go to the quantum efficiency of the defect. So when the defect emits photons, we will lose a lot of signal. So we lose, for instance, a lot of photons that stay inside the silicon because the silicon index is very high. The transmission of the setup is also lossy, and the detector efficiency. Well, in that sense, we are not limited by the detector efficiency because it's almost 100%. We are mostly limited by the collection efficiency. So a lot of silicon stay trapped in the silicon. A lot of photons stay trapped in silicon, and so with all this number, we can access to 50% of quantum efficiency, which is, I mean, this is a lower band, but it's probably higher, so which is a very good single photon source. You can make it faster also by embedding into a nanophotonic cavity. So this is what I'm showing here. So we opted for a nanophotonic cavity, so a photonic crystal cavity, where we remove 3 holes. And the challenge here is to take this center, a single center, and put it inside this cavity where the optical mode is very high. So we need 2 things. So the spatial overlap. So we need the location of this center needs to be at the right place. And also the emission of the center needs to also overlap with the resonance of the cavity. So this is very challenging. I will not go into the details of how we managed to it, but you can think of, we made lots of cavities. So it's mostly probabilistic. So this is a scanning electron micrograph of a successful device. So this is you can see the photonic crystal here. So this is all silicon with where we remove 3 holes in the middle. So it's called L3 cavity. And on the right side, you can see the raster scan, the photoemission scan of this successful device. You can see in the middle of the cavity, there is a bright emission. And this bright emission is coming actually from a single G-center. So we measure to confirm that it's a single center, we measure the autocorrelation function. But in that case, we measured it in pulse regime. So you can see a strong suppression of the zero delay pulse. And when we look at the spectrum, actually what we see is 2 peaks. The first one is the cavity resonance, and the second one is the zero follow line of the quantum emitter. And you can see we achieve here the spatial overlap, but the spectral overlap is not achieved because they don't emit at the same wavelength. They are not at the same wavelength. So if you want to achieve light matter, enhanced light matter interaction, you need both of them to be to overlap. So we added another step is we just basically added argon gas inside the chamber. So and this argon gas with condensate and change the refractive index of the cavity. So this is plotted on the left. So the photoemission spectrum as a function of cycle number. Cycle number is basically the number of steps you put argon inside the chamber. And you can see as we tune the cavity resonance toward the zero follow line of the emitter, you can see an enhancement of the emission. And we managed to achieve up to 30 times enhancement. And this enhancement is really due to Purcell enhancement, Purcell effect, where the lifetime of the emitter decreases. So we managed to decrease the lifetime of the emitter by almost an order of magnitude, from 50 nanoseconds to 6 nanoseconds. So, which is very promising if you want a very all silicon, very fast quantum light sources. So now the third step, maybe I'm going too fast, but that's the format. For the in the second part, I mentioned a small cavity. We remove 3 holes. So the size of the cavity is just 1 wavelength or few wavelengths. Okay. But what if now we want, let's say, a very bright source? Right? So if you want a very bright source, you need an extended cavity. So the brightness of the source, let's say, will scale as the square of the linear dimension. So if you want something very bright, such as a laser, you need a big cavity. But there is a problem when you make it, when you make big cavities. And the problem is that it becomes very quickly multimode. So, and this problem was highlighted since the first emission of laser in 1958. So first of all, so a laser is basically 2 components. There is a cavity, which are represented by 2 mirrors, and a gain medium. And so if you provide energy to the system, you can get stimulated emission, which is lasing. So lasing, light amplification by stimulated emission of radiation. And as I said, so in 1958, the first notional laser, they said single mode may be selected if you have a small, suitable small angular aperture. So they identify a problem where if you want a coherent laser and powerful coherent laser, it needs to be small enough, because if you make it big, then it becomes multimode. And this can be explained very naively using this this slide. So for the when the cavity is small, the distance between modes is let's say 1 over L, where L is the size of the cavity. But as you increase the cavity size, the distance between modes decreases. We see 1 over L2. L2 is bigger than L1. And as you make it bigger, so it makes it very hard to distinguish between one mode to the other. So you lose the coherence. And here, so I just represented the same mirror, but in 2 dimensions. So we have 2 mirrors here, and along X and along Y. And this, the first one is the fundamental mode. And these are higher order mode. And you can see there is a problem, not only about the frequency, but also the spatial location of the mode. Because when you have higher order mode, they will see gain. Basically, they can laze because they see gain where the mode, fundamental mode, is not. You see, for instance, the higher order mode will see more and more gain at the edge, where the fundamental mode is not taking the gain. And so that's a big problem. And actually, people to make high power lasers, so they kind of overcome this problem. They either generate the laser and then amplify the laser using a fiber, or they just make an array of incoherent laser. So each, for instance, for 2D VCSELs, each laser is independent from each other. So it's become incoherent. So if you want really something like coherent, which is very crucial for measurement or for long distance communication, you don't want dispersion, for instance. So the coherence is very important. So the way we did it, actually, is to use the physics of Dirac in the continuum. So we have the graphene type of lattice, but using photons. So these are holes, air holes inside the dielectric, inside the multiple quantum well, the gain. And when you look at the dispersion of this lattice, you can see a Dirac cone. And well, you can notice that the Dirac cone, the radius of the isofrequency contour, the radius of the isofrequency contour is basically the index. And when you are at the Dirac cone, actually the index is 0. And there is lots of consequences when the index is 0. And the first one is that you get a flat envelope. So here we simulated the cavity. You can see for the mode 0, so this is the fundamental mode, mode 1 and mode 2 higher order mode. And you can see the fundamental mode is completely flat, which is very surprising. It's not like conventional Gaussian mode. Higher order mode are really also messy, but you can see that the fundamental mode will take all the gain. You can see there is no space for other modes to lace. And actually, you can see that on the sketch on the right side, that this series emitting laser will emit from all the surface, and all unit cell will participate together to the lasing mode. So we did we fabricated such a device for different sizes and for different detuning from the Dirac. So here we use the radius of the holes to tune the how far we are from the singularity. So for R less and R larger, so we have quadratic dispersion. For R Dirac, we have Dirac cone linear dispersion. For small sizes, we have all single mode, so there is no problem for small size, as I mentioned, because the distance between modes is large enough. But as you increase the size, you see for R less than R Dirac, you get multi-mode, single mode for R Dirac, and again multi-mode for R larger than R Dirac. So it's we also fabricated more sizes, and it stay really single mode for all sizes fabricated so far, which is quite remarkable. So last thing, so saying that this laser is single mode just by looking at the spectrum is not very fair. So actually, you need to make sure that it's single mode, you need to measure the autocorrelation function, which is the G2, but for laser. And you can see that we on the right side we measure the G2 as a function of the pump power, and there is some kind of 3 regime that can be distinguished. So the first one is spontaneous emission. So the G2, so the G2 at 0 is 1. So and if you increase the power, you get into amplified spontaneous emission. What do you get? An anti-bunching, sorry, a bunching, not an anti-bunching. Anti-bunching was for silicon. So there is like some thermal light generated here. But as you increase even more the power, so we get to the lasing regime, then it becomes coherent. And so this transition ensure that it's a really coherent laser. So we have like a very flat G2, and we measure also the G2 for even higher power. So it stays coherent for all power we measured so far. So, so I showed you briefly, I mentioned the discovery of single artificial atom in silicon. So they are very promising because you can integrate them into photonic chip without like heterogeneous integration. So you can build really large scale photonic chips. So we are working on it with international groups to push even further the development of such silicon centers. And we're trying to include also the spin. This is also something that we are working on it. And so for the laser, so we managed to make a scale-invariant laser, but I would say that's not the end of the story. Of course, there is some technological aspect to it, but there is also some physics aspect to it, because this type of cavity with flat envelope and the physics of Dirac can be also applied to other topics, like in cavity quantum electrodynamics, into the quantum world, for instance. So we are also exploring this, but the physics is very rich and there is a lot of work to do. So yeah, I would like to thank all my collaborators, so from France, where I did my PhD, and from where I am now, Berkeley, with Thomas from the Berkeley lab and Boubacar Kanté from the ECS department at UC Berkeley. So thank you for your attention.
All right, super. So thank you very much, Walid. This is fantastic work, very exciting. And it seems like you're basically working at the frontiers of nanophotonics and bringing it to very interesting directions, such as quantum technologies. So, you know, very, very nice work. So we have time for questions, of course. So let's start. So, well, first of all, everyone, please put in your questions into the Q&A box. There are some already, and please don't hesitate to put some more. So let's go and address some of these questions. Okay, so we have somebody that is asking, so Amlan Mukherjee is asking, are there any hints of spin polarization in G and T centers?
So I see that you know a little bit on the topic.
It sounds like
you mentioned the T centers. Huh? Sorry?
It sounds like indeed that this person knows quite a lot.
Yeah, I can read the question. I see some experts in the center already, so that's very great. So, but the spin polarization of G center in particular. So, there is, I mean, in principle, there is a spin in the G center. So it was, actually the first magnetic resonance measured in silicon was with G center, ensemble of G center. But somehow, so we tried actually to measure the ODMR for a single G center, and it looks like there is no spin. So I mean, this is I don't know why, but we are still exploring. So I mean, there is a strategy of pushing more the G center, like looking at the spin of the G center, maybe charge the G center, but also looking at other centers. And you mentioned the T center, and this T center is also very exciting. So it was it's really pushed by a group in Canada, it's the SFU, and they are really the guy who pushes the T center, and it has very nice properties. And about the spin polarization, so I think it has not been measured because they didn't do coherent spin control. They just say, okay, there is a spin, but I think we need to wait a little bit for further measurements. But we need more people into this field, I would say. It's too much for just a couple of groups. Yeah.
Okay, great. Thank you, Walid. So next question, it's about the G2 measurement that you were showing. The question reads, in the G2 correlation, a lot of factors could cause the central dip to be non-zero. So I guess the main question is, why is that? And person is asking, which is Carl Xu, could one of them be the emission from such a silicon defect at our higher photon Fock states, maybe from two defects nearby, instead of a single photon? So
Yes.
essentially, like, yeah, what's the origin of the non-zero G2?
Yeah, that's a nice question. Actually, I think, so you have to remember the way we excite the defect, we use a green laser. So we excite above the gap. And the thing is, when you excite above the gap, you excite a lot of defects, and you excite also the silicon. So, and what we observe is that there is some kind of uniform background. Even if you're not exciting the defect, just next to the defect, there is some kind of uniform background everywhere. And when you correct the G2 by the background that you measure near to it, you get actually G2 of 0. Basically, it means that this G2 is limited by this incoherent background. So the origin of this incoherent background, I'm not sure what is it. I don't think it's another defect because the density is very low. We have one defect every 10 micron. So the probability to get two defects at the same position, I think it's unlikely. I think there is some, as I said, incoherent background, and it has been shown already that you can also reduce this G2 in silicon by using a cavity, for instance, or using quasi-resonant excitation. You excite really the phonon side band of the center, and you can get a very nice G2, like it is done for quantum dot, for instance. But the way we excite the defect is not the best way. So, yeah.
Okay, great. Thank you very much, Walid. There's more than one question asking about the temperature at which you operate your devices.
Yeah, so
are they cryogenically cooled, or they're room
yeah,
temperature?
they are cryogenically cooled, yes. But they can work up to 100 Kelvin. We managed to find single centers that can emit up to, if I remember well, 120, 130 Kelvin. So which is the above nitrogen liquid temperature. Yeah.
But typically, you operate them at
at 5 Kelvin,
I guess,
typically.
or?
Sorry?
So let's say, so you tested at higher temperatures, but then typically with your setup, do you cool down to a few kelvins with the?
Yeah, we cool to 5 Kelvin, and we look at the emission as a function of temperature. We mostly work at 5 Kelvin. Okay,
but would it be the same at, let's say, 10 or 15 Kelvin? Because that's already like a big difference in terms of the hardware.
Yeah, I mean, yeah, so the thing is, you know, when you want to do quantum in general, you want to be at low temperature because you get rid of this thermal effect. For instance, there is this broadening of line width. So if you want to get a narrow line width, you need to work at low temperature. But if you just care about, I mean, I don't know, things like emission of photons, it can work up to 100 Kelvin. But if you care about some more complicated stuff, such as the spin, the T1, the T2 time, you need to work at low temperature.
Okay, great.
5 Kelvin. Yeah.
Okay, another question is asking, does the C defect in silicon produces any other single photon emission in the visible?
So I see another expert here. So you mentioned about the C center, is that right? This is the C center, the carbon oxygen center. In the visible, the thing is there is a gap of silicon, so the gap of silicon is at 1.1 micrometer. So all the defects that we observed were at higher, higher wavelength, so higher than 1.1 micrometer. So in the near infrared, in the visible, it will be above the gap. So I don't know if you can get single photon emission above the gap of a semiconductor. I'm not sure about that. Even for diamond, it's below the gap. So I don't know. Or maybe C defect is another defect that is not the C center I'm thinking about. I don't know.
Great. Okay, thank you. Another question is about the tunability. So you've shown that you can get the emission and the cavity tuned on top of each other by using argon. Is there any other way you could do that? And there's a sequel question to that, but I'll let you first answer the first question.
So your question is there any other way to tune the cavity resonance?
Well, I mean, I know, could you use, for instance, strain in order
of course.
to tune both on top of each other?
Yeah, actually, we have, I would say, a project. So I will not tell all the details, but we use actually MEMS to tune the cavity resonance.
Okay.
So we apply strain to the cavity. That's another thing we can do.
So and then the sequel is, could you, do you foresee a way to be able to find, how likely would it be for you to find two sources with exactly the same emission?
We can also use strain. So we can use strain to tune the cavity resonance, but you can also use strain to tune the emission wavelength. So you can tune both. And so if you want a scalable network, you need not argon, because argon, I mean, you deposit everywhere. But if you use strain, local strain with MEMS, for instance, you can really control all quantum nodes independently. And you can make all the cavity in resonance. You can make all the emitter emit at the same wavelength. So that's something that we, thanks to the silicon platform, we can do actually, because MEMS or this kind of stuff are very mature in silicon technology. Yeah.
Great. Well, just a practical question here is, what kind of generation rates are you getting with the source when you have like the person enhancement? You were mentioning a lifetime of 5 point something nanoseconds. So essentially you can pulse your system and operate at a rate of maybe 10 nanoseconds every time, something like this, right? Is that correct?
Yes, exactly. Yeah.
Okay.
So I mean, there is two things. So we accelerate the emission, but we also enhance the emission at the zero phonon line. So remember, the emission of the center is zero phonon line plus phonon sideband, but this phonon sideband you don't want. You just want one wavelength. So this cavity can enhance by 30 times the zero phonon line, but also accelerate by 10 times the emission rate. So yeah.
Okay. So let's go over maybe a few more questions. We have a question which asks, can you extrapolate your system to longer wavelength towards maybe 20 microns as an example? So really like, change the wavelength quite a lot.
So he's talking about the laser, right?
I'm guessing, yeah, that's about the laser.
Yeah, of course, yes. You can just like you just change the lattice parameters of the photonic crystal and the gain medium, and you can make all wavelength you want. The physics is really general. It's not constrained to one wavelength. Yeah.
Okay. So let's go for another question. Somebody's asking that, okay, you're using green light to excite the infrared transition. Would it be possible to add electrodes to electrically run a device? So
sorry, can you repeat the question?
I guess the question is, you're exciting the source with light. Could you potentially excite it electrically instead of optically?
Yeah, of course, yes. And this is again the strength of silicon, because it's very easy to make a PIN junction. And I mean, there is a project ongoing on this, so I will not tell much detail, but yeah, it's one thing we can do, and we will do for sure.
Okay.
So
we have very good questions, it seems, from the audience.
There's a lot of questions actually. Wow.
Yeah.
Thanks a lot.
Okay, maybe let's stop. Let's not stop, but let's finish with one more question, which is a general question that I find quite interesting. Is somebody's asking, what is the weakness? What are the weaknesses, potential weaknesses of a silicon-based quantum source?
So, I mean, weakness of silicon-based quantum source. So if you want a good, I would say, if you want a good quantum source, you need many things. So first one, you need to have a bright source first that emits lots of photons, but you need them to be indistinguishable, for instance. So very coherent also, quantum light sources, and on demand, and potentially electrically pump. So all this, and actually the best are quantum dots. So the question is, I will reformulate the question: how far we are from getting the performance of a quantum dot? I think we can get there because I mean, there is a lot of potential. So actually the indistinguishability had already been shown a few months ago. Actually, when you see the speed at which this field is growing, it's very fast. Like in 2 years, there's a lot of things happening. And I think if we still continue working on it, we can achieve very bright, as bright as quantum dots with quantum efficiency near unity. And we can achieve narrow line width, for instance, by working with silicon-28, isotopically purified silicon-28. So the line width will decrease by 2 or 3, even 3 orders of magnitude. So, and one problem, so we need to make is indistinguishability between 2 different emitters. That I think this is the main problems. So it has been shown that you can, for one center, emit a stream of coherent photon, of indistinguishable photon, but when you have 2 emitters, it's very hard for them to emit at the same wavelength. So this is really the challenge and the weakness so far. So we need to explore new ways to create them. So we use carbon impulsion, but we can use other methods that are less, I mean, more gentle, I would say, to make a quantum network of this silicon center indistinguishable. So I think this is the main weakness, I would say.
Great. Okay, so let's stop there for questions. I just want to say that there are more questions that haven't been answered, but we will answer them. We will share the questions with Walid, and then Walid can answer the questions afterwards. Also, I want to mention that at IDQ, what we're doing is we're building devices that can be used in such groundbreaking experiments. This is what we do. So we're very happy to have Walid talk about his work and see how you guys are taking science to the next step and how we can be part of this somehow with what we do. And I want to finish, well, there's going to be a poll. Okay, so just 2 quick questions to answer. They're going to appear on the screen. So we'd be very happy if you can answer these 2 questions. And I want to thank you very much, Walid, for spending the time with us and to tell us about this work and answering all the questions. Yeah. So here's the poll.
I see lots of questions. So, I mean, maybe you can send me an email or...
Yes, the questions are going to be answered. We're going to share all the questions. So let me just launch the poll. There you go. We will share all the questions with you, Walid, and you can follow up with these questions. Okay, people are filling in the poll, so thanks very much for this. We'll just wait a little bit, and then we'll soon after finish with that. Great. Okay. So thanks again, Walid. Have a good day.
Yeah,
thank you. Thanks to everyone for spending some time with us, and we wish you an excellent day.